Welcome back to Unit 4. We've been talking about applications of the derivative. We talked about position graphs and then max-min problems and linearization. And today we're moving on to the very last of the applications, which is called related rates. Today's video is going to be about recognizing what related rate problems look like and how to set them up. And then we'll continue in the next couple of days really working on solving them in the nitty-gritty details. If you remember last week, at the end of the week, I introduced you to differentials. And we use differentials to talk about change, specifically when two things are changing. For example, maybe the volume of this sphere and its radius. We can talk about kind of a before and after situation. The radius starts at 10 inches, it grows by this much, and we want to know how much will the volume grow. That was a differential problem because it's relating a change in the radius to a change in the volume. But what's important to note is that we're just measuring one change. It's an instantaneous thing. It's before and after, and that's it. To jog your memory further, you can look at the work. This is exactly what you'd do. You'd write a function, take the derivative, and then use the differential equation. That should be familiar. So this week, we're also talking about change, but it's different. Look at these two questions. I just talked about the first one. Read the second one. How are these two questions different and how are they similar? So there are a number of correct things you could have said here. But what I hope you picked up on more than anything else is that even though both of these questions are basically talking about volume of a sphere and its radius, and they're both talking about change, this one's asking how much, and the second one's asking how quickly. And what that means is that the second question is somehow related to time in a way that the first question is not. This is a change that happens once, whereas this is a change that's happening at a certain rate. That's what makes the second question a related rate question instead of a differential question. You should get really used to listening to those distinctions. Even though the setup and derivative is going to be similar, it's really what the question's asking that guides how you're going to start the problem. So let's talk a little more about rates. A rate is a numerical measurement that describes how something is changing with respect to time. This should sound familiar because we started this whole unit by talking about velocity, and that was basically the rate at which something's moving. But you may be really comfortable saying, oh yeah, velocity is the first derivative, and I want to warn you that that's a little bit too simple. Not all first derivatives are rates. It's only when you're taking the first derivative of something and the independent variable represents time that we have a rate. If the independent variable is something else, you can take the first derivative, but it's not going to tell you how something is changing with respect to time. It's just going to tell you how two things are changing related to each other. Let's see if you understood that explanation. Take a look at the two situations, A and B. In each of these situations, we have an equation or a function that's modeling some quantity, and each of these functions have inputs and outputs, in other words, independent and dependent variables. Which of these two derivatives would represent a rate? Exactly, only h prime is a rate here. V prime is a first derivative that does not represent a rate. Why? Well, look at the independent variable. Here the independent variable is a radius, and radiuses are measured in length, not in time. So since this is not a derivative with respect to time, this is not a rate. The second one, even though we're using an x, not a t, x, what does it really mean here? It really means hours. So the independent variable here is time, which means we take the derivative of a function whose independent variable is time, and we're ending up with a rate. In this case, the rate how quickly the sun is heating up or cooling down. This is such an important distinction that I want to do this one more time. Here are three more. Tell me which one of these represent a rate. Gorgeous. B and C both represent rates. And hopefully you avoided some of the common traps here. Just because there's a variable t in the problem doesn't mean you're necessarily talking about time. In this case, t represents temperature. And even when you have a t that does represent time, it doesn't necessarily make your derivative a rate, because if time's the output, or the dependent variable, then it doesn't count, because we're measuring how time is changing with respect to something else. So it's really about what the independent variable is, and again, t doesn't have to be time. There's plenty of other variables that could be time, and plenty of other things that time could stand for. Now that you know how to recognize when a derivative is a rate, we can talk about what it means for two rates to be related. When two related quantities are changing, the rate at which they're changing must also be related. This should make sense to you. When we have the balloon, which is expanding, its radius is expanding at the same time that its volume is expanding. It's like two different ways to measure what's changing. And we can use derivatives to write an equation that describes the relationship between how quickly the radius is growing and how quickly the volume is growing. Basically, my tip for you is use Leibniz's notation, which again is the differential notation, and you want to make sure that you out loud or in writing interpret what each of these pieces mean. And I'll model that for you, but I want you to guess first. What does dv dt mean? What does dr dt mean? Great, so what you should know right away is this is a derivative, and then what I would have expected you to type in to Edpuzzle is that dv dt is the rate at which volume is changing with respect to time. So not just the derivative of volume, that would have been not specific enough. Specifically, it's the derivative of volume with respect to time. Having heard that one, you probably guess what this one should sound like. This is the derivative or the rate of change of the radius, again, with respect to time. So in order to figure out what dv dt is, we want basically an equation that relates these two. And spoiler alert, it's going to be a very simple equation that just involves multiplying the right thing times dr dt. Those of you who are chemistry students, this actually probably looks really similar to doing conversions with units, and you can really think of it almost exactly that way, at least when you're setting up your equations. What do you think I should put in this blank in order to make dv dt equal whatever's on this side? That may have been a trickier question, but I think you'll see how it works in a second when I tell you that if I put in this blank dv dr, you can imagine the dv will end up on top. The dr on the bottom that I wrote in cancels with this dr, and on this side we end up with dv over dt. Again, it's just like units in chemistry, really. Now, that's not necessarily the mathematical reason that this works, but that's an easy way for you to think about setting up your equations when you're doing word problems. We'll work a lot more in class about the mathematical basis for why this works. Let's start with some simple related rate equations. You're basically just setting something up. Make sure you have this example modeled in your work. And we'll start with example one. We'll actually do this one together. So this is the same situation that we were talking about with the balloon, but I've converted it so that we're really only talking mathematically for a second, and we're not going to worry about the numbers. The volume and radius of a sphere are both changing with respect to time. What we need to do is find an equation that relates dv dt and dr dt. Remind me again, what does dv dt mean and what does dr dt mean? Right, they're the rate of change of the volume and the rate of change of the radius. So our goal is to set up an equation where dv dt is equal to something times dr dt. And as we discussed on the last slide, I can think about what that something is almost like I do units in chemistry class, where you want ultimately volume to end up on the top of this expression and time on the bottom. In other words, the thing I need to multiply in the middle is dv dr. What does dv dr represent? Yes, it's the derivative of volume with respect to radius. Notice how that's a different derivative than this one. They're both first derivatives, but this is a different derivative. It has a different variable, the bottom variable being your independent variable. So even though the reason we wrote this here was because we could cancel out the dr's, that's not actually what we're doing here. What we're doing, our answer should keep dv dt and dr dt and should have an equation or an expression right here in the middle. And we've just analyzed this to understand that the expression I need to put in parentheses is the derivative of a function whose output is volume and whose input is radius. Can you think of what function that would be? Right, that's just the volume of a sphere formula, we know. And we can think about it as a function whose input is r if we want to. So dv dr is really just the derivative of this expression, which we can find just using normal power rule. It's 4 pi r squared. And so now 4 pi r squared is the same thing as dv dr. And I'm going to plug that into this expression, which gives me an equation that relates dv dt, the rate of change of volume with respect to time, and dr dt. And this, again, looks probably really similar to the differential equations. And I want to acknowledge that they look similar, but emphasize that they're not the same. The differential equations would have just had dv and dr. And that would have been an equation that allows you to estimate how much volume is changing when it makes just a sudden change, a one-time change. This is not talking about a one-time change. This is talking about how quickly volume is changing, and it's changing over the course of time, continually. And so the setup looks similar, but the meaning is really different, and you will need to be able to explain the difference between the two. Anyway, this is your answer ultimately, at least if the instructions are just to find the equation. Ultimately, you would maybe plug in an r value and a dr dt speed to figure out exactly how quickly volume is changing. We'll do those after we practice a couple more setups. So look at example 2 and example 3 and see if you can follow the same process. Basically, you want to come up with an expression that relates the quantities they're talking about. So example 2 should have been fairly straightforward. What we know is the rate of change of volume and we're looking for the rate of change of volume, and we know the rate of change of a side. And so you just set up the differential, and I figure out what needs to go in this spot by thinking about how I could make this side equal dv dt. Well, I need dv on the top, so I put a dv on the top, and I need to get rid of this ds, so I put ds on the bottom so that they'll cancel, and that would make both of these sides equal each other. Now, that's not actually what I'm trying to do. That was just my thinking process for filling in the blank. Then I interpret what this means, and dv ds means the derivative of the function whose input is s and output is v, in other words, volume and side length. And so I just find the formula for the volume of a cube, and you have to know we're talking about a cube here. And then I take the derivative, which is just 3s squared, and that's where my answer came from. Example 3 might have been slightly more difficult, and maybe you got this far in your setup and then got stuck. And that would make sense to me because it's kind of difficult to figure out what should go in this blank. Obviously, we need a v on top, but if you think about it, we need a dr on the bottom and a dh on the bottom, and we're not supposed to end up with 2 dt's on the bottom. We need just 1 dt on the bottom, so somehow one of those needs to go away. There is a way you could kind of think your way through this reasoning process, but I'd actually rather show you a slightly different approach that we could take. There's another way we could set this up, and it has to do with kind of implicit equations. So backtrack with me for a minute and think about, in example 3, what is the actual function or relationship we're talking about? Right, we're talking about the volume of a cone. So what do you know about the volume of a cone? Exactly, we know the formula, 1/3 pi r squared h. So when the problem says that the volume and the radius and the height are changing with respect to time, that means we can think of these as functions. And they're all functions that depend on time. So I could even kind of rewrite this formula to look like this. And again, I'm not actually changing the formula. I'm just reminding